Section 5-9 is on the volume of a solid by plane slicing. The objective of this section is given a solid whose cross-sectional area varies along its length. We want to find its volume. And the technique that we're going to learn here is going to be very similar to the technique that we saw in the last section. The only difference is in the last section we were finding area, but it still applies in the method that we're going to use to find the volume. All right, the first thing that we need to talk about is numerical integration. This is actually not a topic that's covered until the next section, but it'll help us in some of the calculations that we've got to do here if we know this method. So numerical integration, anytime you see the term numerical, it's talking about using your calculator to evaluate something. So we've seen how you can use your calculator to find a numerical derivative. That's the nderiv command. There's a similar command on your calculator that allows you to calculate a numerical integral for an approximation of a definite integral. And so here is that command. If you want to calculate the definite integral from a to b of f of x dx, your calculator has a command that allows you to do that calculation. Does an approximation for it, but it's a pretty good approximation. The name of the command is fnint. It's under your math menu, right below the nderiv command. And in parentheses, you specify four things. The first thing you specify is your function f of x. That's the same as with nderiv. The second thing you specify is the variable of that equation. And in this case, it would be x. That's the same for nderiv. And then finally, for this command, you have to specify the lower bound and the upper bound. So you specify a and then b. With nderiv, you just, of course, are finding the derivative at 1 point, so you only have to indicate one value there. All right, so that's our nderiv command, or the fnint command. Let's just use that here real quick on an example to illustrate how we use it. You basically, just like nderiv, are not going to write down fnint. You're still going to use the formal notation here with the integral sign and the differential dx and so forth. Do not write down fnint. But if I'm trying to integrate, for example, the definite integral from 1 to 9 of x squared dx, I can use my calculator to evaluate this. And it's pretty much understood that if you just simply have a definite integral and you say it's equal to something, then you've used fnint to do that. So let's go under our math menu. And all the way at the bottom there, it's actually number 9, zero solver, is fnint. And so our function in this case, let me just move this box over so I can see that again. Our function was x squared. Our variable was x, which, by the way, if you had your function typed into y1 or any one of your y equals variables, you could have said y1 instead of x squared there. And then your lower bound is 1 and my upper bound is 9. Put a closing parenthesis on that and we get 242.667. And so that right there is the definite integral from 1 to 9 of x squared dx. All right. So that's using that command there to quickly evaluate a definite integral. And we're going to use that here in this section because of the fact that we've got to set up some pretty complex integrals. And rather than having trouble with fundamental theorem of calculus and evaluating that correctly, we're going to let this help us do that. Okay, this in essence kind of takes place of the fundamental theorem of calculus. Gives me an approximation, a very good approximation. All right, so let's jump into the technique that we need to talk about in this section, which is finding the volume of a solid by plane slicing. And what we mean by that is you're going to slice this solid, just like we think about taking a definite integral and slicing it into strips or rectangles to find the definite integral there. We evaluate it to, or find the area of each rectangle to evaluate that definite integral. Same thing is true here, except we've got a solid, so it's a three-dimensional shape, and so I'm going to slice that into these plane slices. All right, so let's illustrate this with an example here, and we'll kind of go through the steps of what we've got to do each through this process here. But a typical kind of problem that you're going to see is you'll have some function that's bounded on some interval. So I'm just going to take some function like this, we'll say, is our function f of x. And most of the time, they're going to say that you're going to take that solid there and you're going to rotate it around some axis. So you might rotate this around the x-axis, for example. And of course, if I do that, then I'm going to end up with some sort of a shape that looks like this. I'm going to try to sketch this in 3 dimensions. It doesn't really matter if you can't do that. That's fine if you can't. It's kind of helpful sometimes if you can, but if you can't, that's no big deal. It looks something like this. It's been rotated around that x-axis, that original region there. This guy right here was rotated around that axis. And when it rotates around there, we end up with this 3-dimensional shape. And the technique that we're going to talk about is how to find the volume of this solid here that we end up with, or for that matter, any solid whose cross sections are uniform, or the same shape. Might not be the same size, but same shape. All right, so let's go through the process here. The first step is to slice the solid into flat slices, or strips as we called them in the last section. Flat slices with uniform cross sections. That's the key to this whole part, that I have to have uniform cross sections. In other words, they all have to be circles, or they all have to be squares, or they all got to be triangles, or whatever. They all have to have the same uniform shape. Now for our problem here, it's going to be perpendicular to our axis of rotation. And actually, for that matter, any problem that involves a rotation like this around an axis, then your slice is going to be perpendicular to that axis. On problems that don't involve a rotation, they'll describe which direction you have to slice this in order to get a uniform cross-section. So I'm going to come back up here to our original slice and just draw in, or excuse me, our original region here, and just draw in one slice here of this. Let's say that we took that section right there and we're to slice it. And what I want to do is I want to end up taking that slice and I want to rotate it around this axis and end up with what that slice looks like when I rotate it around. And this is really the key piece, is I got to be able to sketch what the slice looks like. It's not so big of a deal if I can't sketch the entire solid, what it looks like, but I at least need to sketch that slice. And you can tell that it's this circular shape here. It's actually, I guess, a cylinder, with the fact that it's got a circular base and a circular top, and it's a solid here. So it's actually a cylinder that we end up with. Okay. All right, so we want to draw one slice that represents all the other slices, and we've really done that there. You can see that that one slice, no matter where I sketch the slice there, it's always going to be circular. And it just depends on where I slice it as to how big it is, but we're not talking about the size of the slice, it's just the shape of it, as long as it's representing all the possible slices in that region. And that, in fact, does. All right, and the next step is to mark the key sample points on the slice. We saw this in the last section where we marked the bottom and the top, or the left and right of your strip there that you had. We'll do that same thing here. I'm going to go ahead and name these 2 points here. We'll name this point right here. And this point right here, we'll call this x, y, 1. And we'll call this x, y, 2. Notice I'm naming those on the original slice. All right, so the original slice are the points that I name in 2 dimensions. And then I can use those to help me figure out the volume of that slice that I have there in 3 dimensions. All right, so we've marked those key points. And then the next step is to use geometry to find the volume of the slice, dV, in terms of your sample point. So in the last section we used dA because it was representing the area of one of those strips. Here we're using dV because it represents the volume of this one slice. So in our problem, if we were to calculate what dV is, I'll do this in blue for the same color as this slice that we have here. Notice that the slice in this case has that, like I said, a cylinder shape. It's got a circular base and top, and it does have a height to it. So BV, of course, is equal to the area of a cylinder in this case, which I know is pi times my radius squared times height. That's my formula that I use to find the volume of a cylinder. So to put it in terms of the variables that I have here, I have pi times my radius. The radius of this thing, if I were to mark that, this distance right here is the radius. That's r. So that's just a vertical distance. It's really the difference in those y values. So r is actually y2. Oops. I'll do this in the same color there. It's y2 minus y1. It's the difference in those y values. It gives me the radius of this slice. And it's the radius squared, so it's that quantity squared. And then times the height. Now you can see the height, or the thickness of this, if you want to call it that. This right here is the height from here to here, is the height of this thing. Notice that that's the same as the thickness of my original slice right here that I drew in, my original strip in that red region. And that's a small change in x, so we call that dx. Dx is that height. So we'll put in dx as our height. All right. And then, of course, depending on the problem, you would plug in what y1 and y2 are. In this case, y2 falls on the function here, f of x. So I'll go ahead and plug those in. That dv is equal to pi times y2 is on my function, f of x, minus y1. You can see y1 is down there on the x-axis. That's 0. And then, of course, it's squared there because it's the radius squared times dx. And I get this in terms of x and dx. Pi times f of x quantity squared dx. We'll just get rid of that 0 there. Now, it doesn't always turn out to be 0 there. It depends on the problem. And obviously, it will vary from one problem to next. But in this case, that lower bound there, that y1 was 0. All right? So we get a differential equation, much like the differential equation that we saw in the last section. You can see it's a little bit more complex because it's not just dA equals base times height. There's a little bit more to it here, but it's basically the same idea. Come up with the equation that represents the, in this case, volume of that one slice, and then plug in your values to get a differential equation in terms of x and dx. All right, use algebra to find dv in terms of one variable. We've kind of done that with our example there. We got it in terms of x and dx. And depending on the problem there, depends on how many steps there you've got to go through in order to get it in terms of one variable. And then the last step here is to use some calculus to add up all of the dv's and take the limit. And we use that same terminology with the dAs that we talked about back in the last section, that we added all those up and took the limit. We're talking about a Riemann sum. The same is true here. And so that Riemann sum, when you take the limit of it, you're actually integrating. So we're just going to integrate the equation. And so if we go up here to our equation that we had, we would end up integrating dv, which of course is going to be v. We integrate pi times your function squared times dx. And on the right side, we use a definite integral. So I have to figure out how far from on the left and right do I want this original slice to go, which in our case, it would slide all the way over here to x is 0. And all the way over here on the right, I'll just call this b. Maybe, in fact, I'll just call these a and b. It might not be 0 every time that they set up that interval, so I'll just call them a and b. So our limits of integration then down here are from a to b. All right. Again, the process is definitely a little bit more complex, but it's very similar to the process that you saw in the last section. All right, let's try a couple of examples here. Take a look at example 1. We call this the disk method. As you saw there in that illustration, you end up with a flat slice there that looks kind of like a disk. So that's the reason why we call it that. It says the region under the graph of y equals x to the 1/3. I'll write that function down. Y equals x to the 1/3 from x equals 0 to x equals 8. Oops, x equals 0 to x equals 8. Is rotated about the x-axis. And I like drawing a little circle here with a little arrow there. It's in a circle and indicating the axis of rotation, just so I remember the right axis there, around the x-axis to form a solid. write an integral for the volume of the solid and evaluate it to find the volume. Assume that x and y are in centimeters and show that your answer is reasonable. All right, so the first thing I want to do is start out with a sketch of this thing. You could use your calculator to sketch what this looks like, but I know it's a standard power function here with a exponent less than 1. It looks like your square root function. I know kind of what the shape of this is going to look like, so I'm just going to sketch it here. So you've got some sort of a curve that looks something like this, we'll say, and this is our function y equals x to the 1/3. And we're going to rotate this around the x-axis, they said, so around our x-axis. And when you do that, you're going to end up with some sort of a shape here. So I'm going to go from 0 to 8. I'll mark those as well. There's 0. We'll say that this is 8 right here. So when I rotate it around that axis, I'm going to end up with some sort of a shape that looks kind of like this. And again, it doesn't matter whether you can sketch the what the solid looks like there. The important part is that you can sketch in there this one slice. And I'll name these 2 points. I'm going to call this point down here x, y, 1. And I'll call this point up here x, y, 2. And then rotate that slice around that axis of rotation. So we're going to rotate that around the x-axis, and we get this shape right here. That's that disc that we said there, or it's a very short cylinder is really what it comes down to. And now what I need to do is write the volume of that cylinder. That's what I need. I need the volume of that slice. So I want to find out what dV is equal to. Now, so again, since it's a cylinder, I know the volume of a cylinder is pi times the radius squared times height. And I would start out by writing down that formula every time. Whatever you're trying to calculate the volume of, write down that formula for the volume of that shape. And then fill in what you know from your sketch. So dV is equal to pi times, now the radius, in this case, is going to be this distance right here is our radius, r. So that's a vertical distance. It's the difference of those y values, y2 minus y1. And that's the radius squared. Times h, which h for us is this height right here. We'll draw it right here. That's h. It's an h. But that turns out to be the same as the thickness of the original slice. So the thickness of your original slice here from here to here is dx. So dx is actually the height of this thing. So we'll put dx as our height. Now, if you look at the differential tells you what variable you need to get this in terms of. So I have dx here, so that tells me I need to get rid of the y1 and y2 and replace it with x's. So we have dv is equal to pi times, for y2, go back up to your sketch and look at where y2 is at. y2 is on the curve. And on that curve, y equals x to the 1/3. So we're going to replace y2 with x to the 1/3. And then y1 is on your x-axis. The x-axis is where y equals 0. So we'll replace y1 with 0. And that's, of course, this radius squared there times dx. So now we've got it in terms of x. Let's just simplify this one last step. You don't necessarily have to because we're going to use our calculator to evaluate it and not fundamental theorem of calculus. But let's go ahead and simplify this as much as we can. X to the 2/3 squared is actually, excuse me, x to the 1/3 squared is x to the 2/3 times dx. And actually that one wouldn't be too bad to integrate with fundamental theorem, but I want to illustrate using that numerical integration feature on your calculator. But now that I got my differential equation and it's in terms of one variable, we're ready to integrate this thing. The only thing we need is limits of integration over on the right side. So look at your sketch here, and I want to think about how far do I want to slide that blue slice or that green cylinder all the way to the left. And you can see that would come in at x equals 0 right here. And how far do you want to slide it over to the right? And they actually gave us that value. That was over here at 8. So they actually gave us those two values in this problem. That's nice when they do that. They don't always do that, but they did in this case. So it's from 0 to 8. And on the left side there, when you integrate dv, you get v. And on the right side, like I said, if you wanted a little more practice with fundamental theorem of calculus, you could certainly use it there. I want to illustrate your numerical integration command. So let's use fnint. of x raised, oops, it's pi times x raised to the 2/3. Make sure you got parentheses in there, of course. My variable is x, and I'm going to integrate from 0 to 8, they said. And it'll take a few seconds here to crunch that. And we get 60.319. Now, if you wanted to find out, most of these are going to be some nice multiple of pi, because I used pi in my formula, pi times the radius squared times height. So if you take that answer and divide it by pi, you get 19.2. So the answer, and I know there's a little bit of round off error there, that's illustrating for you the slight error that you have with FNINT, very, very small error. This turns out to be 19.2 pi. And you can write it either way, of course, doesn't matter to me. And both of these, they told you that the units for your x and y axes were in centimeters, so since we found volume, these would be in cubic centimeters. Cubic centimeters, cubic centimeters. Both of those are obviously the same quantity, so they have the same units. All right, and that's how we evaluate that problem there. They said to go a little bit further with this. It says also to assume x and y are centimeters and then show that your answer is reasonable. Okay? And by the way, some of these problems are going to say to use fundamental theorem of calculus, and I want you to use FNINT. Okay, so you can ignore some of those problems that if they say to use FTC or find it exactly, I'm expecting to use this numerical integration technique. Now, to show that your answer is reasonable, let me show you a couple ways that you can do that. On this original sketch here, what I could do is I could draw another geometric figure, actually a couple of geometric figures in here, find their volumes, as long as they're nice shapes that I know volumes of, find their volumes and at least get a window as to what seems reasonable for this problem. For example, if I were to sketch, let me just sketch on top of here. If I were to sketch this cone right here, I'd have the exact same size base, but obviously it fits inside of our solid that we were working with. If I were to find the volume of that cone, I would know that the volume of our solid that we are working with must be bigger than the volume of the cone. And for the volume of the cone, I know volume is equal to 1/3 pi times the radius squared times the height. So that's 1/3 pi times the radius squared. The radius in this case is the radius at x equals 8. When x is equal to 8, the y value there is 2. If you want to mark that, this is y equals 2 right here. So the radius is 2 squared times the height is the distance along the x-axis there. That was 8 units. All right, so you get 2 squared is 4 times 8 is 32 divided by 3 times pi. And so we'd end up with 32 over 3 pi. And if you want to punch that in your calculator, 32 over 3, I'll just quickly punch it in here, times pi is 33.510. 33.510. So I would know that my answer has to be more than that, and we were. Okay, we were at 60 something, so we were definitely bigger than that. Now the other thing I could do to get kind of an upper bound is I could take and say, well, there's this cylinder right here. If I rotate that around, I know I'm getting a lot on the sketch here for you. Has the same base over here on the right side. There's that cylinder with a height of 8 and a radius of 2 that is definitely more than the solid we were working with, whose volume is more. So if I found the volume of this green cylinder that I sketched, that's pi r squared times the height. So that's pi times my radius again is equal to 2. And my height was 8. So it turns out we end up with, again, 4 times 8 is 32. We get 32 pi in this case. Notice it's 3 times the volume of the cone there. And 32 pi, if you punch that into your calculator, 32 times about 3, that's going to be 96, well, a little bit more than 96. What do we get? 100.531. 100.531. Again, so what this does is it gives me a range. I know that my answer has to be between 33.5 and 100.5, basically is what that tells me. And since we got an answer that was 60, that's at least in the ballpark. I still don't know if that's the right answer, but it at least is reasonable. And again, they'll ask you to check that your answer is reasonable. I'll let you do that for some of the problems. You don't need to do it for every single problem, but I definitely am expecting you're checking your answer as you go in the back so you know you got the right answer there. All right, let's take a look at one more example. Example 2 says to rotate the region about the y-axis this time. It says the region in quadrant 1 is bounded by the parabola 4 minus x squared. Y equals 4 minus x squared. And it's rotated about, and it's also in quadrant 1. I should indicate that we're in quadrant 1, so it's only the region in quadrant 1. Rotated about the y-axis. And it's formed a solid, or to form a solid paraboloid, find the volume of the paraboloid if x and y are in inches, and show your answer is reasonable again. Okay, so we'll add units onto this thing, but let's first take care of a sketch of this thing. And we're rotating around the y-axis, so let me give myself enough room to sketch this thing. So it's only in quadrant 1. 4 minus x squared is a graph that looks like this. It crosses the x-axis at 2, the y-axis at 4. And we're rotating around the y-axis here. So we're going to rotate around this axis. All right, so if you want to sketch what that solid looks like, it's going to look something about like this. Here's what our paraboloid looks like. Again, it's not so much a big deal if you can't sketch what the solid looks like, and these are starting out pretty simple as far as the sketch. They'll get more complex as you go. But what is important is that you sketch your slice and then rotate it around. Now again, remember that your slice is perpendicular to your axis of rotation. So our axis of rotation is the y-axis, so that means our slice this time is going to be horizontal. So we're going to end up with a slice that looks like this. We didn't talk about that, or didn't worry about that as much in the last example, but you do want to be perpendicular to your axis of rotation. All right, and I'll go ahead and name these points here. So this is going to be, we'll say x1, y, and this will be x2y. And like I said, we're going to rotate around the y-axis, so the shape that you end up with looks like this. When we rotate it around, you get that same disc or cylinder shape. And we want to find the volume of that cylinder. So again, start out with our formula for the volume of that disc we've got there. Volume is pi times the radius squared times the height. So dV is equal to, replace r with what it is. R is, again, this distance right here. When I measure this distance right here, that's r. So in that case, it's a difference in my x values. So it's going to be x2 minus x1. That's the radius squared, so it's x2 minus x1 squared. And then the height of my cylinder is this height right here. I'll just mark it right here. That right there is the height. But again, notice that corresponds to the same height of the original slice that I drew here. And that's actually dx, or excuse me, dy. It's a change in y values, not a change in x values. So that's a dy. So my height this time is dy. All right, and again, look at your differential in this problem. It's a dy, so that'll tell you what variable you want in your problem. I want y's in there, so that means I got to get rid of x2 and x1. And so if I come back up here and look at what x2 and x1 are, x2 actually falls over here on my curve, so I need to know what x is equal to. So let's take that equation that they gave us and solve it for x. If y equals 4 minus x squared, I'll solve that over here on the side. If y is equal to 4 minus x squared, then solving for x, I'll have x squared is equal to 4 minus y, and so x is equal to, technically you get plus or minus the square root of 4 minus y. And the negative part of that is over in the second quadrant, because x is negative over there. We only want the positive part of that, so the x2 will get replaced with that. So it's pi times the square root of 4 minus y. And then take a look at x1 now. x1 is on the y-axis. That's where x is equal to 0. So x1 is 0. And of course, it's that quantity squared. It's the radius squared times our differential of y. And again, let's just simplify this a little bit. Actually, it turns out pretty nice there because you're taking that square root and squaring it. So it's actually just 4 minus y dy. All right, we are all set to integrate this thing now. So we have the integral of dv is equal to the integral of pi times 4 minus y dy. And we just need limits of integration here. So go back up to your sketch, and you got to think about how far up and how far down do I want this slice to go. So let's deal with the lower bound first of all. I want it to come all the way down to the x-axis. So that's where x is, the x-axis is where y equals 0. And I want that slice to go all the way up here to the very top of this parabola, which is at y equals 4. The key there, realize that since we're talking about a differential of y, that means I'm looking for y values this time, not x values, but y values. So I want to integrate this from y equals 0 to y equals 4. And we are all set to integrate this. Again, this one wouldn't be too bad to use Funwell theorem on, but I want to illustrate your program or your numerical integration feature on your calculator again. So let's use it. And so FNINT of pi times 4 minus, now you could put this in terms of x. I'll go ahead and put it in terms of y since that's where you wrote it as, but there's nothing wrong with saying pi times 4 minus x. Doesn't matter what variable you use, as long as you indicate that same variable right here. That's what the second term there is for, the second argument. And then you specify the lower bound, which we said was 0, to our upper bound of y equals 4. And we get 25.133. And again, if you want to see what this is as a multiple of pi, you could take and divide that by pi. When it turns out that's equal to 8 pi. Again, for a lot of these problems, especially when they're these cylinder problems and you're using the volume of a cylinder that involves pi times the radius squared times height, your answer is going to be usually a nice multiple of pi. It doesn't always end up that way, but usually you're probably going to find that. And they also said here that x and y are in inches, so since we found volume, this would be inches cubed. So pay attention to that. If they give you a unit there in that problem, use it in your answer. All right, and they said check your answers reasonable. You could do something similar to what we did in the last example. You know, sketch a cone, sketch a cylinder there, and at least gives you a window, a range there that you know is reasonable. All right, and that's as far as we're going to go in this section for right now.